Welcome to our session on KVcache, a central bottleneck in large language model inference. Today, we'll explore why the KVcache is crucial, the costs associated with it, and why optimizing it is a primary focus for all major LLM advancements. This deep dive is part of our ML Systems Interview Guide, aimed at helping you understand the complexities and optimizations in modern machine learning systems. Let's get started. In this slide, we examine the difference between a superficial and a comprehensive answer regarding KVcache and autoregressive generation. The surface answer highlights that KVcache stores keys and values to enhance inference speed. However, the full answer digs deeper, addressing why we cache keys and values but not queries, the memory implications of KVcache, and why it's a central bottleneck in inference. Understanding these aspects provides a more complete picture. Welcome to this slide on autoregressive generation. At each step of decoding, the model generates one token at a time. The query for this new token attends to all past tokens using dot product attention with their keys. It then calculates a weighted sum of their values. Here, the query is the current token, while the keys and values consist of all previous tokens, expanding as more tokens are generated.
This slide highlights the critical asymmetry in processing efficiency. On one hand, we have low efficiency and high redundancy without a KVcache, leading to quadratic runtime. Generating each new token requires recomputing key and value for all previous tokens, increasing redundancy. On the other hand, using a KVcache, we achieve high efficiency and low redundancy by computing only the current keys and values, eliminating unnecessary recalculations, and optimizing performance significantly.
This slide explains why we cache K and V, but not Q. At each generation step, Q is used only once for the current token and is then discarded, so there's no point in storing it. On the other hand, K and V hold all prior context and are needed at every future step. By caching K and V, we avoid repeated projections over a growing history, making the process more efficient.
Let's explore the cost of using KVcache. While it enhances performance by trading memory for computation, it isn't a free gain. For a single request with typical large language model parameters, we need about 2.5 gigabytes of memory. Scale this to 64 users, and the requirement jumps to over 160 gigabytes. This exceeds the capacity of an A180 gigabyte GPU, highlighting that KVcache size limits how many users you can serve at once.
Let's explore the two stages of LLM inference, prefill and decode. In the prefill stage, the full input prompt is processed in parallel to generate the initial KVcache. Here, the bottleneck is the compute power, so adding more flops speeds it up. The decode stage, however, generates tokens one at a time and reads the entire KVcache from memory each step. Its bottleneck is memory bandwidth, making it more challenging to optimize. In this slide, we explore why the decode process is memory bandwidth bound. Each decode step involves calculating just one dot product, which is minimal arithmetic work. However, to perform this calculation, the entire KVcache must be loaded from high bandwidth memory into the GPU's compute units. This results in the GPU being mostly idle, as it waits for data to arrive. Consequently, arithmetic intensity is extremely low, while memory transfer demands are extremely high, leading to severe underutilization of the GPU. Welcome to the optimization landscape for KVcache. The goal across all major optimizations is to reduce the KVcache size, boosting throughput and concurrency. First, multi-query attention allows all heads to share a single set of key value projections. Grouped query attention lets groups of heads share keys and values, balancing quality and memory. Quantized KV stores key values in INC8 or INC4, cutting memory usage by 2 to 4 times. Lastly, paged attention uses OS-style paging to reduce memory fragmentation and enable efficient batching.
Welcome to our discussion on the chain of impact. At the core, optimizing the KV cache is crucial for enhancing LLM serving systems. When we reduce the cache size, we unlock higher system throughput, enabling more concurrent requests and lowering memory usage. This optimization has a direct multiplicative effect on real-world serving capacity, making it the highest leverage problem to tackle. Let's delve deeper into how each of these elements contributes to overall efficiency.
Let's dive into the key takeaways. First, Q is single-use while K and V accumulate, benefiting from caching. Unlike Q, the KV cache is large, scaling with users using about 2.5 kappa weeds per request. With 64 users, it can exceed an A100's memory. Decode processes are memory bandwidth bound, meaning the GPU waits on data rather than calculations. Therefore, all optimizations focus on reducing cache size to improve throughput, using techniques like MQA, GQA, quantization, and paged attention.